Alrighty, welcome back, everyone. Today I'm joined by Professor Emilie Ringe of, now at the University of Cambridge, who is a professor of chemistry, kind of in the metallurgy, I guess material science, but also kind of you research a lot of based on like spectroscopy and stuff like and physical chemistry based. But we'll certainly hop into that in due good time. So thank you again for joining us on the podcast. Perhaps for us to get started, we could, start with a little bit of your background so the audience can get to know you a little bit. I saw you, apparently you have a Wikipedia page. I don't know if you knew that, but I was scrolling through it.
Yeah.
And
well, it's also wrong. So this Wikipedia page was done by, and I'm sorry, I'm going to switch my internet. So I'm currently on my Wi-Fi, but I have a plug here, and it's going to be a lot better for that connection.
Okay.
So let me do that.
Okay.
And it will disconnect us for.
Yeah. Well, so what I'm going to do is I'm just going to pause it. So hang on 1 second. But we're back though. But yeah, so you're saying that the Wikipedia page is wrong. So that's kind of that's interesting.
This Wikipedia page was done by essentially someone who's looking at people who won specific awards. So I think this comes out of my C&E News Talented 12. I think that person just looks at everyone that gets those and makes a Wikipedia page without searching too much, it seems. I appreciate to have a Wikipedia page, but I'd like to point out that I am not American and I am Canadian.
Yeah. I was going to say, oh yeah, that's a huge... Well, this is where it gets crazy. So it says you're an American chemist, but it also says in your early life you grew up in Quebec. So I don't really... I don't know.
I could have naturalized and become American.
Maybe.
Yeah.
I don't know. Maybe, I don't know. Because you started at Rice, I guess, to start your early career. I guess maybe that's what they're referring to. I don't know. But anyways, yeah, you are.
I spent a large amount of my academic life, Ph.D. and early career in America. There's nothing, wrong with that.
Well, you are.
Canadians are touchy about this.
Yeah, no, that's okay. Yeah, I get it. I mean, you want your nationality to be right, No, but yeah. So that being said, you did say you're Canadian. You grew up in Quebec. So
yeah, that's
I feel.
I grew up just south of Montreal, speaking French, and went to McGill. Sorry?
Like Montreal is a fluently speaking French, right?
That's right.
Okay.
On the island of Montreal itself, most people will also speak English, but if you leave the urban center, English is a bit more rare. And I definitely was able to say just about yes, no toaster when I was 16.
So you spoke like English. Wow. So from up until like high school, basically, you barely spoke English?
Yeah, I mean, we had English course in high school, but they were of such low quality and, memorized sheets of vocabulary kind of level.
Yeah.
There was no opportunity to practice because, I lived in a town where there was no English. And so it was a real uphill battle in my undergraduate, which I took in English, to really adapt to, to living and thinking and doing science in English.
Mm-hmm. That's really fascinating because, I mean, obviously, I think Americans think of Canada, obviously, like, there are neighbors English speaking, but that's pretty interesting that, like, but I guess what if you go to like the sticks of Canada? Is that still French then, or is it kind of mostly English? Like, I mean, like middle nowhere, like something like, I don't know, Albuquerque. Like, I don't know. Is that French also? Is it really just kind of the Montreal, Quebec?
The Albuquerque equivalent.
Yeah.
No, so I mean, most of Canada is of course English speaking, and then there's just that province of Quebec, which was a French colony really to start with, where there's a couple million people that are French speaking, and there's that it's that little island really surrounded by A, the rest of Canada, and B, the United States. But the culture is very strong in the province of Quebec. We make our own movies, we make TV series and whatnot, and there is there really is a national pride and a culture in the French speaking that's going on there, and a number of French speaking universities. Even if you if you want to do your science in French, which I thought, well, for an international career, I'm kind of going to have to do this in English. Like,
that's really
cool. And I think that's a sentiment that is that is seen across the world. Perhaps not in America, where people take it for granted, but most of the rest of the world has to learn English.
I know. That's kind of. I mean, obviously, like living in America, we have a lot of freedoms, obviously, and that's a great place to live. But not being able to really not knowing a second language is certainly like one of the crux. But unless you live kind of in California or Texas, maybe you can learn some Spanish for sure. But yeah, I mean, overall though, it's really just English. Quite unfortunate, I think. But yeah, no, actually, that's super cool that you speak French and English. Do you speak any other languages or?
I learned a little bit of Spanish when I was at school, but it's sort of funny. My brain doesn't deal very well with three languages, and I somehow can only deal with the basic language and then the other language. And when I knew three, I kept confusing at that time English and Spanish, my two second languages. And it was a bit of a nightmare, and I learned that when I was a teenager, and I forgot most of it, and I'm a bit afraid that if I were to try to learn a third language, this would happen again, in a sense. So really now a few words of Spanish only.
Yeah, I was listening to a podcast. It was like a scientific podcast. They were saying that if you are a graduate degree in STEM, whatever it is, you basically speak a third language though anyway. So like PChem in itself is probably a third language. Like honestly, like the amount of words you learn is just like its own language.
Okay, well, so next time someone asks me that question, I'll say yes. I guess science.
Yeah, that's a good one. Yeah, I would say that one.
Yeah.
But so in Quebec, I mean, kind of growing up, were there activities and hobbies that you like to do, or things that interest you, kind of growing up?
Yeah, I did lots of downhill skiing, so I'm quite sporty. I grew up in quite a sporty household, and then I started doing, going to the gym when I was a teenager, and doing sort of Thai boxing and these kind of things. And that really kind of followed me through, and now I've run about 10 marathons. I kind of do one a year.
10 marathons? Wow.
I've done a number of triathlons, and I think that was really due to the interests of my family and just activity and sport activity. I never really did tons of sort of, I don't know, intellectual activities when I was in high school. Funny enough, there just wasn't that much that was of interest to me. I don't know. Not that I was not a nerd. I was a total nerd, but I was a sporty nerd. just to be clear, don't think I was popular. This is not.
No, that's a trend nowadays. I think there are a lot of like really smart athletes. I think for sure, like people in my circles for sure, that are really smart, but also happen to be sneaky athletic too. So, no, I definitely hear that. So I assume you began with maybe running cross country, and then that kind of grew into like longer distance runs, like marathons, half marathons, stuff like that, or.
I never really did short distances.
Okay.
I was just really interested in sort of 10K to start kind of thing.
Yeah.
And quickly built to marathons. Did a bit of triathlon in between, but that's too much kit. Like a triathlon's kind of too complicated.
Yeah, it's very. I mean, I know the training. I know the training for a marathon by itself. I mean, to train for a marathon, like that's a lot of work, and then to throw in like training your body to cycle, and then also swimming. I think swimming is that's sneaky. Like I mean, that's super difficult. And you have to swim something crazy, right? For triathlon, it's like 3 miles. How long do you have to swim for?
Yeah,
Is it
so
that long?
I've to the half Ironman, not the full. And in the half Ironman, yeah, you swim 1.5K, so a mile.
1.5, yeah,
And
that's a
then
long mile.
you cycle something like 56 mile, and then you run half a marathon,
Yeah.
so
Like
30
just the
miles.
training. I mean, where do you find it? I mean, to find the time to train for that is just, it's like, you know,
Yeah, yeah,
but,
and this is why I went for marathons, which actually take much less training
mhm,
because there's not three sports to train at.
mhm. But so do you keep up with like your marathon training? Maybe not like obviously like not right this second, but like, like let's say after you get like, moving over to Cambridge, so you just kind of keep up with that or?
Yeah.
Oh,
I
awesome.
still
Okay.
do. I still work that into my schedule.
Mm.
And Cambridge is great because it's flat and it's never really too cold or too warm to run. So
Oh, that's
actually a
awesome.
really good running place.
That's awesome.
Yeah.
So I guess did some running kind of growing up, but moving into well, I know you
Mm.
did your undergrad at Northwestern. So what drew you? That's at Chicago, I believe, right? So, what drew you to attend Northwestern? Well, actually, no. I think you did you transfer from somewhere though first? I forget. I think you did actually.
Yeah. So
Okay.
I was at McGill, um,
Okay.
where I actually did most of my undergrad there, and then got a 1 year internship at Merck, the pharma company, sort of in between my junior and senior year at McGill, and then after that decided to move to Northwestern. They had a really really good program in physical chemistry
Hmm.
and inorganic chemistry, which really really interested in me, and that segued me into actually doing my PhD also at Northwestern. And when I started my PhD, I already knew everyone, and I already knew where to get everything and how to navigate the research system in the chemistry department at Northwestern. And it meant that I finished my PhD really quickly because I had basically a head start.
Right. That's really cool. Um, on that though, so you started though. So yeah, like you mentioned, you did an internship at Merck, which is obviously kind of more like organic based, like organic chemistry. Um,
Well, I was in the formulation at Merck, which is really chemical engineering.
okay, I see. Okay. So
It's
what?
not organic synthesis. Yeah.
Right. Okay. Okay. I got you. Okay. It's like flow heat transfer kind of scale up type stuff or formulation chemist. So
That
what did you
kind of
do?
stuff, like
Okay. Yeah.
pressing pills.
Right. Okay. Okay. That must have been really like awesome opportunity to do that. And um, for
Yeah, and it really it made me see what industrial research looked like,
mm,
and what industrial research, with and without a PhD looked like. And, it really convinced me that, I wanted the job that the PhD level people had. And so,
I'll go back in here. So I think we were talking about your internship at Merck. You're kind of more of a formulation chemist, kind of more on the engineering side. But how did that? I guess what I'm really curious about is how did that transition then into like studying inorganic chemistry, which is what I think you were doing at Northwestern. I think.
yeah, that's right.
Yeah. Yeah.
So the work at Merck was really a formulation work. So how do you get from what the organic chemists make to a tablet, a pill,
Mm,
some form of dosage, right? Which is again really sort of a chemical engineering type problem. And I dealt with lots of spectroscopy types there, and it kind of intrigued me to learn a bit more about spectroscopy and about about the chemical engineering like. And when I started at Northwestern, of course Northwestern is very very strong in inorganic chemistry, physical chemistry,
yeah.
nanotechnology, and that fits very well with these interests that I had developed with spectroscopy. Like how can I use cool instrumentation to basically discover the world? And I ended up doing a little bit of inorganic synthesis and ended up eventually joining really a physical chemistry spectroscopy type
Right.
group for my PhD.
Yeah. So during I guess real quick on your I guess your bachelor's slash master's degree, like we mentioned, you were at Northwestern. You're working with Professor James Ibers, I think is how you pronounce it. But
That's right.
you were looking at kind of uranium complexes, like
Yeah.
uranium particularly bounded to like first order transition metals. And so I guess what I'm curious about is I'm not really familiar with this area of research. So, what was the purpose of looking at uranium bounded to transition metals? I mean, whether or not it had applications or not, I don't know. But like, what was kind of the purpose for this?
I'm sure someone would find a number of applications, but actually, what I was interested in, and again, right, that's a master's project, is actually the electronic structure of the uranium coupled with the metal. And what happens in uranium is that you have 5f electrons, and these can behave really differently depending on what you're bound to. So you can have really, really itinerant electrons or very localized, and that can lead to a number of electronic properties. And by changing that bonding, by hence changing the other elements that are there, and especially bonding with 3D electrons, then you can create really cool electronic states.
Okay.
And obviously, as a master's student, I basically just did the synthesis, but it taught me really useful skills of Schlenk-Klein glove box, ovens, X-ray diffraction, these kind of things, which became useful for the rest of my career.
Extremely important. Yeah. I guess real quick on like uranium chemistry, because you're working with it. I mean, I feel like a lot of, even kind of myself, I don't really know much about uranium chemistry. But, I feel like casual people will hear uranium and think, oh my God, like radioactive decay, radiation. I mean, is it really like that deep? Like, I don't know. I feel like there's a lot of misconceptions maybe about uranium, because I've heard, even here at the University of Houston, people are working with uranium, and it's like not, I mean, it can be dangerous, but like, I don't know. People kind of take it out of context, I guess. So I don't know. I don't know if you want to blame me on that.
Of course. I mean, uranium is associated with radioactivity, but remember, like when you look at one element, there are many isotopes of that element.
Right. Okay.
And some of them are much more radioactive than others. And so what the chemists work with is depleted uranium. It's uranium that basically has the most stable isotopes in, rather than what you might think of enriched uranium, which is the stuff you make bombs with.
Okay. Right.
And
okay.
so it's all about which isotope formed the majority of your stuff.
Okay, that's really cool then. Okay, so then transitioning then from your undergrad to now PhD. So I know PhD at Northwestern in organic chemistry, like really stellar division. It was kind of a natural progression to stay at Northwestern. Like, what kind of were decisions to stay there instead of like branching out?
Yeah, there was a lot of thinking done there because, of course, in America, everyone is told, well, you need to do your bachelor somewhere and your PhD somewhere, right?
Yeah. Sheep
and
thinking.
it is just it's just really ubiquitous. I sort of wanted to stay in the Chicago area. I had moved 2 years before. I looked at University of Chicago, who offered me a place also. I looked at Northwestern, and they're both fantastic places. But Northwestern had a little bit of an edge in terms of the type of science I wanted to do, the sort of more applied nanotechnology, sort of slightly more sort of physical chemistry. University of Chicago, don't get me wrong, had a fantastic program. Tough decision. But I stayed at Northwestern because the type of science, and in hindsight, Northwestern has been really at the forefront of that type of science ever since.
Right.
Before I joined, after I joined, and has continued being a a producer of faculty members and of really interesting discoveries in physical chemistry, inorganic chemistry.
Right. So So during your PhD, that was kind of really your introduction to plasmonics. Then, how?
That's
So,
right.
so I know you worked with Professor Richard Van Duyne and Laurence Marks, and and like I mentioned, so you're kind of using nanoplasmonics for like looking at particle studies, particle optical studies. And so I guess what I'm curious in is how were you kind of introduced to this idea of like plasmonics generally? Because I'm sure I don't know, I'm sure it might be a daunting task at first, but how was this idea kind of given to you to do research on?
Yeah. I mean, as you know, right, when you're a first year PhD student, you basically don't know anything. Okay. And I absolutely got myself into that. I was like that also, right?
Yeah.
And I was looking at a variety of different projects. I wasn't necessarily sold on plasmonics itself, but Rick and Laurie, my two advisors, had this idea for a project that was going to be joined with them. I liked both men very much. I liked their groups, and I thought, okay, well, that seems like a good environment for me with lots of lots of resources, lots of instrumentation, lots of cool ideas. And I was like, well, I honestly don't know anything about plasmonics, but this seems to be an interesting collaboration.
Right.
And
That's
I sort
awesome.
of threw myself. And it's always a bit like that, I feel, when you choose research topics. Like,
right.
They kind of happen to you a little bit. There's a little bit of element of randomness.
Right. I hear that. Yeah. It definitely especially like first, second year. I mean, you really don't know. It's funny. It's like when you come out of like undergrad, you think you know everything. Like, so it's like you got your bachelor's degree and you think you know everything. And then you graduate school and you're like, oh my God, I know nothing. I always remember that humbling experience for me, but
you know something. Yeah. But you know something different, right? In undergrad, you should get out of an undergrad with knowing the basics of physics and so on, right?
For sure.
Whereas in grad school, you need to know hands-on how to do research. Completely different.
Right. But yeah, so like you said, though, I mean, for the research, kind of just comes to you, I think, for sure. And especially like when you're early in your career as a graduate student. But I guess probably should have started with this first, but I'm going to let you kind of explain plasmonics. I kind of get the basic principle, but I'm not going to sit here and act like I'm by no means an expert. I just know the definition of plasmonics. I don't know anything else really, but I'm going to kind of let you maybe explain the idea of this phenomena.
Absolutely. So basically, I work on nanoplasmonics. Okay, what plasmonics that happen at sort of in nanoparticle. And essentially, you think of a metal ball, okay, like a nanosphere of metal, and it's a stiff lattice of positive ion, and then this cloud of delocalized electrons, okay. And then imagine putting an electric field to that cloud of electrons. Well, it will polarize the cloud of electrons. Now, light is an electric field. Light is an oscillating electric field, and if you think about that cloud of electron interacting with an oscillating electric field, you can imagine there's going to be a frequency at which you can excite the bouncing up and down of that cloud of electrons. And that frequency is the plasmon resonance frequency. In the case of a nanoparticle, it's called a localized surface plasmon resonance. Okay. And it really just means that that cloud of electron oscillates at the same speed, if you want, or oscillate with the oscillation up and down of the electric field of light of a certain frequency.
Okay. Actually, I didn't know light was a magnetic. I was real quick. I didn't know light was an electric field. Is that what you said? I didn't know light was a.
Yeah.
I guess.
So it's
I guess it kind of makes sense actually.
Field.
Yeah. Okay. Actually, that kind of does make sense now that I think about it. Okay. That's really cool.
And that means that these particles can absorb light, can scatter light, and it creates a strong electric field around the particle. And then you can think about doing a whole bunch of things related to absorbing that light, or related to scattering that light, or to enhancing the field.
Right. Okay. And we're definitely gonna return to this though, for sure. But during your graduate degree though, let's see. So yeah, so we're looking at nanoplasmonics, and then so how did this kind of shape your thesis then? Like for the plasmonics and then optical, to do like particle optical studies.
Yeah, so I started thinking. So at the beginning of my PhD, basically, the two advisors were like, "Well, the goal here is to correlate, right, at the single particle level, that shape of nanoparticle, right, which really turns into the shape of that electron cloud, right, whether it's a cube or rod or whatnot, with its optical response. Again, single particle level." And so that was always the goal. And most of my PhD thesis was really on a systematic understanding of, okay, if you have cubes and they go through a different size, different shapes, here's what happens to this plasmon resonance frequency, which color they interact with. And then if you have triangles, if you have hexagons, if you have, so there's a lot of that in my PhD thesis, because it was at the very early on of plasmonics where experimentally people hadn't done that. I mean, now you'd say, "I'll do this," and people would be like, "Well, that's trivial." Okay, but 15 years ago, it wasn't trivial. And so that sort of systematic approach shaped about half of my thesis. And then I became interested in, well, why do these particle shapes occur anyway? Like, why is this silver cube a cube and not a triangle and not a dodecahedron? And there are theories of that. And during my PhD, I basically developed a number of numerical models to actually model the shape and predict the shape of particles, and build that in graphical user interfaces and so on and so forth. And so that kind of merged together into a PhD thesis, which
that's really cool.
Was almost well stitched together. Almost.
Yeah. I know generally like kind of the life of graduate kind of changes the day to day, but like maybe something that I'm even curious about is like, what is it kind of like, what was your day to day then? Like, what is it like? What do you like? I'm finding it hard to imagine. I know it's a lot of spectroscopy, but like I'm finding it really hard to imagine. Like, okay, where are you in the lab? Where, like, what are you grabbing? What are you like? What are you measuring? You know what I mean? So can you give us a sense of like what you're actually like doing? Because I have no idea.
Yeah. So, I mean, to do that kind of research that I did in my PhD thesis, right? I would be, getting to my collaborators, getting a vial of a sample of nanoparticles. My group now makes nanoparticles, but when I was a PhD student, I did it. Arriving in a very dark, big microscopy, so optical microscopy lab, making a little sample in a glass slide, putting that on, and then looking at this microscope for hours and hours and hours, catching single particles one at a time and recording their spectrum, and moving the microscope and recording their spectrum. That was before hyperspectral optical spectroscopy was common.
Oh, man.
So it was really one particle, and then taking that sample into an electron microscope, and that afternoon putting it in and finding those same particles and taking images, and then spending the next day on your computer sort of tapping away to correlate, well, okay, how big is this silver cube, and what is its spectrum, and then and then turning that into some sort of conclusion about the effects of size and shape and so on.
Right. So I guess, like you mentioned, I guess between when you were a graduate student up until now, there's been a lot of research in nanoplasmonics and plasmonics in general. I'm not gonna pretend to understand I know the literature, but to be fair, I think a couple weeks ago we actually had, I forget, he was a Russian chemist, I forget his name, but he was in plasmonics. He gave a seminar at Houston. That was kind of my introduction into this kind of field. I wish I remember his name. Maybe I can go pull it up and find it in a second. But
Okay.
but in any case, yeah, it's really fascinating field. So I guess you know, at the like what I'm losing my train of thought here. This has never happened. I'm trying. What was it again?
Well,
On the
through my
plasmonics.
PhD and now there's been lots of advances in plasmonics,
Yes.
and there was a
Yes.
question.
Okay.
Yeah, coming
Yes,
up.
that's okay. That's what it was. Thank you for having me. Sometimes I get a little distracted. Yeah. So what was kind of like not known about like plasmonics, and then like how has the field, let's say, progressed in the last, let's say, like 10 years? Is there kind of any like general
Yeah,
obviously we're still learning,
there's
but
been times. Yeah, so I think in the applications of plasmonic, there's been a large number of essentially new discoveries, or at least new interests in this application, and how actually having particles that can interact with light means that, hey, you can interact with light. Why not actually capture light's energy and do something with that energy? And that's
mm,
been the the hot topics, no pun intended, in the last basically 10 years in plasmonics. And
we
we
have a
have a
fighter.
very we have a bit of a fight, here, huh?
All right, yeah.
Okay,
Yeah, so we were just discussing kind of the advancements, let's say, last 10 years of plasmonics. So kind of, I guess, more application driven, but I'll kind of let you take the reins on that.
yeah. So in when I was a PhD, which is 15 15 years ago, I guess now, uh, we were still sort of trying to understand the fundamentals of plasmonics. Of course, the theory was all there, but experimentally trying to control, trying to harness, trying to make sure that the level of theory was good for complex shapes and so on. But really, in the last 10 years, people have started, just realizing that if you have a particle that interacts with light, it means that you have a captor for light, and you can do something with light's energy. And really, people are thinking about things like photothermal cancer therapy, where light can induce heat. There's a lot of talk about plasmon enhanced catalysis, where sunlight ideally induces heat, but also creates sort of hot electrons, so-called, basically sort of electron hole pairs that can then do chemistry.
Mm-hmm.
And there's been really interest in these two, sort of above and beyond just understanding, well, what does a cube look like? Okay.
Right.
so how do we actually turn the energy of light into something useful using plasmon particles as antennas?
Right. That's really cool.
Yeah.
So after your graduate degree, you had gone on to become a, I guess, postdoc or research fellow at not where you're appointed now.
That's it.
So full circle. But I guess a question I had then is, was it at this point you were thinking about becoming a professor, or was this kind of like really where you wanted to go with it?
Yeah, that really is where I wanted to go with it. In fact, when I was at the last year of my PhD, my PhD advisors convinced me that I should go to academia and I should probably apply for faculty jobs right away. And I did. And I got through the interview process with a few schools, but of course I was pretty green. But and then I got a limited number of offers at that point, and I decided that I'm actually I have time. This is not a rush. I don't have to jump on the first offer. And I had this amazing opportunity to go to Cambridge on a super prestigious fellowship. And I decided to take that instead of jumping in right away into a faculty job. But I really knew what I wanted to do at that point. And my last year of PhD was really eye-opening. I felt much more independent. I felt like I was actually driving the projects at that point. And it made a huge change for me between, being a student and to being the leader of the project.
Right.
And that was really satisfying. And it made me think, okay, academia
You could
sounds
do
great.
this. Yeah.
Yeah.
It definitely sounds like a natural progression for sure.
Yeah.
But yeah, so I mean, research fellow at University of Cambridge. Wonderful opportunity there. What were your research interests at the time? Are they kind of similar as to what they are now, or what were you kind of initially interested in?
Well, I went to Cambridge to basically learn advanced electron microscopy. So
Okay.
my host there, or my PI, if you want, there was Paul Migley, who's probably the most prominent material science electron microscopist, definitely in Cambridge, and their group had started to work on mapping plasmon resonances with an electron microscope. And so I was like, well, this is real. And they had done silver cubes. So imagine, I was like, I've done silver cubes. You guys have done silver cubes, completely different techniques, end up with similar answers. And I was like, well, this sounds like a really good opportunity to come and learn a new technique on materials that I know, right, and expand my horizons a bit. It was a wonderful time. I unfortunately only stayed a year because, I got basically an email from Rice University telling me that they had a position and I should apply. And I did apply. I got the job, and Rice was on top of my list of places I wanted to work at because it had tons of really good people in plasmonics, and it was in Houston, which I love. And so I ended up spending only a year out of 3 years of funding that I had. But hey, you jump on the opportunities when it comes.
I was gonna say not many like, especially with the way the faculty market is, as far as I understand. Like when a position like that opens up, you kind of have to take it.
Well, when a position opens up at the university you've been basically wanting to work at, not gonna wait 2 years, right?
Mm-hmm. I didn't know. So what about Rice kind of like was like really up there for you then? I'm not familiar with I know they have a great chemistry department, but like I'm not really familiar with, I'd say, the spectroscopy area.
At the time, when I got hired, they were just about making their department of material science. So they were creating a new department. Mm-hmm. And they were creating this new department with an injection of money, where they were going to buy electron microscopes, really set up the facility, which I ended up setting up. And there was a concentration of people in plasmonics that had been hired over the past 15, 20 years. There were some very distinguished faculty and a bunch of new people, and they really felt like there was this sort of critical mass of people coupled with an infusion of new hires and money from the central Rice to develop this new department. Mm-hmm. And so it felt like just the right time.
Right. Yeah, that's really fascinating. But so then spent a few years there, and then I assume position opened up back in Cambridge, and so you know what, why not? So let's do it. That's really awesome. So I guess now we can hop into research that you do now. So broadly speaking, again, kind of plasmonics and plasmonic driven processes, but kind of using like electron and light microscopy to understand the optical electronic properties of like crystals, basically. So I don't know if you want to kind of maybe give us a little overview of your kind of research interest, and then we can kind of go and take a each section.
So I continued being interested in plasmonics, and I thought, well, it's a pretty crowded field by then, right? It was already a big field when I was a PhD student. Yeah. And it has grown and grown and grown because we know more about it, and there are more and more applications coming in focus. And so just before I moved to Cambridge, I had this idea of, well, what other materials can we make plasmonics out of. It turns out it's not as simple as I said earlier. It's not just that it takes a ball of electron cloud, okay? Not all electron clouds are created equal. And it turns out only about, I don't know, 6-7 elements in the periodic table sustain plasmon resonances that are strong, that are in the visible region, which is what you're interested in anyways. You want to do sunlight, something, right? And so at Rice, my colleague Nanomaterials and I had done quite a bit of work with aluminum, which is a good plasmonic, and is very abundant, right? It's, most of the plasmonic people work with silver and gold, which are really rare. And so when I started moving to Cambridge, I was like, well, okay, what other metals are there that are good plasmonic and are abundant? And it turns out magnesium is wildly abundant, as you can imagine, and it's plasmonic in the visible range, and in the UV and in the IR. Okay, and so it's a really fascinating metal. Very little work had been done on this. I think people are scared because you probably heard me say magnesium, like, oh my God, that's going to blow up. It turns out it doesn't. We can make nanoparticles. They sustain a tin surface oxide that's self-limiting. I can dry these nanoparticles in air, leave them there for 5 months, and come back, and they're still metallic. And they are plasmonic. And we've really we've created a lot of the fundamental science of magnesium plasmonic, but also kind of going back to what I did when I was a PhD student, we learned that magnesium makes different particle shapes, okay? Because magnesium is a hexagonal closed pack metal. It's not face center cubic like all the other metals. Basically, we make nanoparticles out of. And so we had to go back to these types of shape construction that I had developed while a PhD student, apply that to these, develop, the understanding of completely new shapes, develop syntheses, do single particle spectroscopy. And it really felt like this was a wonderful platform to use all the techniques that I had at my disposal and that I knew how to use as, that I learned through being a PhD student and a postdoc and so on. And so that's really a lot of our science now. We make magnesium particle, we look at their plasmonic, very fundamental plasmonic property, but also we're interested in the applications because the path is there for applications of plasmonic, whether in sort of cancer treatment or whether in catalysis and so on. And it's only a small jump to think, well, okay, magnesium can do that. And so we've, over the past 5 years, this is basically what we spent our time doing, like thinking how, from top to bottom, how do we deal with magnesium structures?
Right. So I think, those are, I guess a few questions about that then is, are there, so I guess the initial interest in plasmonics, like you said, were kind of silver gold because, I mean, they're rare earth metals, but they are very easy to work with, though, as far as I understand. Like they're super easy to work with. So if you want to start somewhere, they're a good starting point. Are there general what are the general trade-offs, let's say, between, let's say, the inherent properties of like gold plasmonics versus like magnesium? Are there any like general trends in their reactivity and what they can do, or
yes, obviously, reactivity is a big one, right? So, if you want to make a sensor in water, well, perhaps magnesium is not your best choice. Okay, I'm sure I'll claim that I can make a protective shell and so on, and yes, you can. But gold won't react in water. Okay, so that the reactivity of magnesium mostly towards water at low temperature is a drawback, of course. There's also, it also is resonant in different regions of the spectrum, and that's actually a real advantage. So with gold, you can't actually get resonances in the UV, and with aluminum, it's kind of hard to get resonances in the red region of the spectrum. And most metals have basically regions where resonances are damped by other processes within the metal, okay, by interband transitions, by things that basically, if you give energy to the metal, this is what's going to happen, rather than an oscillation of electrons. Magnesium is pretty free of these mechanisms at the frequencies around near UV, the visible, and near IR. So it means that it can sustain resonances across a really broad range, and
Okay.
that's pretty unique.
Yeah.
So there's a bit of a, as you say, a trade-off on a bit of reactivity with water, but it's very tunable. It's very, very cheap, right? and it forms shapes that are inherently different because the atoms are packed differently within the crystal.
Yeah, I guess I'm looking at a periodic table because I'm trying to remember. I know magnesium's like column 2, row 3. You know, I guess 2 valence electrons. But I guess so. Magnesium and gold and even silver, like they're so vastly different just in the atomic size, right? Just their nucleus size. So I find it. I don't know, like what. I guess the point of this question then is like what what are desirable characteristics of, let's say, the atoms that would make them good for plasmonics? Like why not, like for me, like why not iron? Like iron's the most abundant first order transition metal. Like why not iron? Like, you know what I mean? Like, so like what kind of makes a good plasmonic?
Yeah, so it doesn't come down to really just the nuclei.
Okay.
What makes a good plasmonic is the behavior of the electrons within an extended solid.
Okay.
Okay, so we're not thinking about one atom; we're thinking about the metal as a whole and its behavior with respect to essentially an electric field.
Okay.
Okay, and this business of polarized, by the electric field that I mentioned earlier, this is actually what you're looking for in these metals. Okay, and so basically you're looking for lots of polarizable electrons.
Right. Which gold is great at.
Well, yeah, exactly, right. Which gold and metals in general, of course, this basically needs to be a metal. It needs to have delocalized electrons. Metal with lots of delocalized electrons, and on top of that, you need a metal with lots of delocalized electrons where there are no other loss mechanisms. Okay, so for instance, if there's a band transition where if I got a green photon in there, it would promote an electron from a low band to a high band. Okay, even within a metal, there are bands, right? It's not just sort of semiconductors. And if you had that process, then your material would just absorb that photon and make that process instead of having a plasmon resonance. So you have to have polarizable electrons and a lack of other loss processes. Okay, and that's encoded in the dielectric function, the real and imaginary part of the dielectric function. And then you can look at these and say, okay, well, this material fits the requirements to be plasmonic.
Right.
And again, there's just a handful of metals. So you're looking at sodium, potassium, magnesium, aluminum, copper, silver, gold, and then, indium a little bit. Okay, and that's kind of it.
Okay. So
yeah.
I guess, so then why, that makes sense, but like, so kind of, can you like walk me through this sense? So like why not, I don't know, rhodium or like cobalt then? So like what sort of processes would happen in theory if you like were to try to make these plasmonics? Like why, like what would happen like physically?
If you made a nanoparticle just of cobalt, okay, well, you wouldn't make a particle that has a plasmon resonance indivisible. On top of my head, I don't know which failure mode cobalt has, okay, but it's either that the polarizability of the electrons is not sufficient, or there are again loss mechanisms in indivisible.
Okay.
They might be plasmonic. Some metals that I didn't mention are plasmonic at different wavelengths. Okay, so I think
Okay.
lithium is plasmonic in the deep IR. And that just means that the frequency of oscillation of these free electrons is actually very low, so very low energy.
Okay, that makes sense.
Right. But really, I'm considering things that would be decent plasmonics in the.
All right. Something that's interesting to me is that from like an organic point of view, organic chemistry, we know gold is very polarizable, but magnesium does not strike us as, it's a very, from an organic point of view, it's kind of a hard metal where it's not polarizable. It's very hard, and it's a, from a hard sulfides to base chemistry, it's a hard metal and it's not polarizable. So I'm kind of fascinated by this idea that no, you actually could. So I don't know, maybe you can enlighten us a little bit more on those details.
Yes, I think you have to take your hard stuff base kind of chemistry with a bit of a grain of salt, because a lot of that comes from magnesium 2+.
Right. Oh yeah, you're right. Yeah, you're right. Yeah. That's right.
Right. And so these two electrons are not bound very, very tight.
Right.
And on top of that, of course, you have to think, okay, well, again, this is not a one atom process, but it's a collective process of the metal itself, and of how the valence electrons in the entire extended structure behave. And so there's these two things that kind of challenge the conception of the hard acid, hard base kind of.
Yeah, you're right. So then the nanoparticles you're making, then, are they strictly like magnesium 0 then? Are these kind of the okay.
So they're magnesium 0, and then they form about 5, 10, maybe 15 in some cases nanometer MgO layer.
Okay. That's really cool. Okay.
Yeah.
And then I assume when you put them in the atmosphere, they make metal oxides, but are they kind of robust then for, I don't know, atmospheric conditions? Like, I don't really. That's some.
Yeah. So the oxide layer actually does not. Well, it's basically self-limiting. Okay. And so in air at room temperature, we have dried powder of that stuff that we've had for 6 months, and they're still metallic inside the oxide shell. And then the behavior at high temperature is a bit different. We are writing a paper on that just now, but basically up to close to the melting point, even in air at high temperature, they are really rather stable, which is quite remarkable. And you wouldn't believe how many times I get I get this kind of question of what's the stability from reviewers or from conferences and so on. And we've learned to put that to the first and foremost in all of our papers and all of our talks, because it's an obvious question. Like, of course, magnesium's reactive. How do you deal with that?
Yeah, especially like magnesium 0. I want oxides right to magnesium 2. Yeah, so that's really cool. So some other questions I have then is, we've talked a lot about, you spend a lot of time with spectroscopy, right? You have to characterize these materials. Perhaps maybe we should, discuss, electron microscopy a little bit, and light microscopy, right? So how do these instruments work? and what sort of information can you get from those tools?
Yeah, so the very, very basic optical microscopy we do with these structures, and there's a ton of advanced approaches you can take, but the easiest thing to do, okay, is basically to scatter light of one of these nanoparticles. And so if you have your particle here and you come with light at an angle, and then you collect at a different angle, you're only going to see light if it gets scattered, and everything else around the particle, or where there's no particle, is going to be very dark, because you're not actually collecting your incident light. That's called dark field microscopy. Okay, not quite imaginatively, but there you go.
Okay? Keep it simple.
And it's just a very basic scattering microscopy, and it's brilliant because there's no background, and all you see is the scattering from single particle, and you can see actually the scattering from single nanoparticles doing that. And so that's really the key to correlating the structure of these particles with their optical properties, okay, by looking at one at a time, really, that silver cube, right? What color is it?
Mm.
So that's that's kind of the basic concept. As I mentioned before, when I was a grad student, I moved the microscope stage and took, one particle at a time. Now we actually acquire an entire field of view, all the wavelengths, all the particles, and it takes, half an hour.
Right. Let's go.
And then the data analysis is more involved, but
Yeah.
Things have changed. And so that's really our sort of bread and butter technique. Of course, we do a number of other spectroscopies, and we use, surface enhanced Raman spectroscopy, for instance, and so on, to look at other properties. But just to characterize the actual plasmonic behavior, dark field spectroscopy is our tool of choice.
Right. Okay. I guess so. The last thing I kind of wanted to ask you about then is, kind of the applications. I know we were kind of discussing a little bit beforehand for like cancer therapy and for, I guess you would say like kind of, I guess you could say green energy or like, for, I think that's certainly fair. So how did these kind of work then in principle then? So how would it work for these sorts of applications then?
Yeah. So again, right, as I said, when I started talking about magnesium, the path is already beaten for a lot of these applications. Okay, so in cancer therapy, there are currently trials. There's been a few human trials even on using gold nanoparticles to do that. We're just thinking, well, magnesium could work really well also because magnesium is biocompatible. And right. So this kind of field, this is a huge field, right? Hyperthermal cancer therapy with plasmonic particle. It's just enormous. And what this field does is basically you inject nanoparticles either systemically or really at the point of tumor, and then irradiate with a near IR laser. The near IR laser is not absorbed by your tissue; it's just absorbed by the particles. Things heat up. Cancer dies, boom. Okay, really, really, really helpful.
Sick.
To cancers that are not too far from the surface, so that they're addressable with fiber optics and so on. In terms of the advantages of magnesium to do that, no one cares that magnesium is cheap. Like if you have cancer, it's not a gram of gold. That's but
big pharma
magnesium actually dissolves. Yeah, no, but magnesium actually dissolves in your body, which things like gold don't really. Okay, and so that makes a big difference.
Right.
And then in terms of sort of green energy, well, then energy actually cares about the cost. Okay.
Yeah.
The only reason we don't have green energy is because it's too expensive.
Right.
And thinking you're going to do green energy with gold and silver is a non-starter.
Yeah.
Because the energy that will be produced will not be, economically acceptable. And so you have to look at really, really cheap metals. And there's a great quote from I can't remember his name. It's a professor at Harvard who gave a seminar at Cambridge a couple of years ago, and he said, "If you want to make it dirt cheap, make it out of dirt."
Yeah.
And this is what magnesium. It's just dirt, okay?
It is.
And so for these kind of energy applications where you need tons and tons and tons of that material, then this is a real prospect.
Yeah. How would you? The last thing is how would you store it then? Is it possible to store this or is it kind of like as soon as you? I guess another question is if you irradiate the material, it does what it needs to do. Do you have to recycle it? Is it recyclable? I guess I don't really that's one other thing I had is Like, how many times
Yeah.
can you
So
pulse it?
in oh yeah, you can do that forever.
Okay.
That, it's not, yeah, and these materials, typically the type of green chemistry people think about with plasmonic is to drive a chemical reaction,
Right.
a small molecule reaction, right, on at the surface of these particles, and basically use the particle as a transducer between photon to electron.
Mm-hmm.
And then these electrons, do their job at, helping, break down molecules and so on and so forth on the surface. Okay.
Yep.
And so it's really just a transducer, a catalyst, which is present and helps turn, again, sunlight into an energy in another form, or into more concentrated electric field that drive chemical reactions.
Right. That's really cool. Well, Professor Ringe, I want to thank you so much for coming on the podcast. It was excellent to hear from you. And on the plasmatic devices, I'm always enlightened by this.
I hope you and listeners learned something.
Yeah, I definitely will. If anything else, yeah, absolutely. So, well, thank you again for listening on today, and see you in the next episode.